Non-record.
Yeah. But you stopped midway. So like when this process is on Windows, at least you will have 2 video files. Okay.
Yeah, but the other one is junk. I mistakenly selected record to cloud. It's not okay.
Oh, okay.
Stop it and record on this computer. Yeah, I don't know what the cloud thing and how easy it will be access the video from there. Okay. Okay. So anyway, for the purpose of the recording, let's just go back. So we have the classical probability distribution, okay, which is an n tuple. We usually return as a column vector, p1 to pn. So probability distribution means these numbers are greater than or equal to 0 and they add up to 1. And the quantum analog are density matrices. So these are n by n complex Hermitian matrices. They're positive semi-definite with trace 1. Okay. And then we have the notion of taking product probability distribution. So if a probability distribution P on the system A, Q on the system B, denoted by these probability vectors, the product probability distribution is on the system AB, okay, and it is denoted by this, lexicographic ordering. So the least significant coordinate is for Q or on the system B, and the most significant coordinate is on P or the system E. Okay, this is. And analogously, we will now see what is the notion of taking product density matrices. So this will become the tensor product of density matrices. Okay. So let's see. Yeah. So let me. So there is an arbitrary element rho ij out here. So this is on the system A tensor. It's an arbitrary element sigma kl out here on the system B. And now so this is defined similar to this lexicographic ordering. So let me write it down. So the ij element rho ij multiplies this matrix, which is sigma. This is on the system A. So this is defined to be the tensor product of two matrices. So the definition holds for general matrices also. They don't have to be positive semi-definite or anything like that. So tensor product, also called the Kronecker product. Okay, so this is right now. This is the tensor product, also known as Kronecker product after the mathematician Kronecker. Matrices. So this is the definition element wise. So it's very similar to this definition, as you can see, like there would have been a pi here, and the pi would have multiplied the entire vector Q. So instead of pi, we have rho ij out here. Okay, it is in the ijth position, but now this gets multiplied by the entire matrix sigma. So the question is, what is this consistent with? So this is consistent with our definition of tensor product of vector spaces, okay, which we had defined earlier. So let us recall. So what was tensor product of vector spaces? So suppose A is the span of some computational orthonormal basis. Remember, we single out some orthonormal basis in each Hilbert space, in each inner product space, and call that the computational basis. And I mean, these terms will make more and more sense very soon. Why is it called computational basis? So this is AM and this is BN. This is the ket notation, which emphasizes that these are vectors, column vectors, if you want to explicitly write them as tuples. And we have defined A tensor B as the formal span of AI tensor BJ. And remember, I goes from 1 to M, and J goes from 1 to N. So this was the definition, and so I hope you recall this, the notion was formal span. And then any vector in the formal span, I'll say, is a vector in the tensor product space. And if I have to write a vector in the tensor product space, of course, I mean, now it is formally defined as a linear combination of these symbols. So if I have to write this linear combination as a tuple, we have chosen a certain ordering, which was nothing but the same lexicographic ordering. So if I take a vector V in the tensor product vector space, so this V is equal to summation ij, some complex number Vij, AI tensor Bj. So if I have to write it as an n tuple, so normally I would write this V. So this is on the system AB. I'm representing that. So I write it as Vij. But again, the least significant coordinate is J, and the most significant is I. Okay. So it's reminiscent of this lexicographic order here. So that is the ordering I will choose out here. And with respect to this ordering, if you recall, we have defined, I mean, we have calculated what is tensor product of two vectors. So let us say I take a vector x a. So this is summation I xi ai y b, which is summation j yj bj. So in terms of n tuples, if I want to write it as column n tuples, this will be x1 to xn in the system A. And this will be y1 to yn on the system B. So then I have defined the meaning of this vector xa tensor yb, right? So the formula was the obvious one you would guess, right? Ai tensor b. But then if I write it as an n tuple, so what would I get? So I would get something like xi out here, and it is multiplying the vector y. So as you can see, this is exactly the same thing as what I did out here. So to make it smaller so that you can see it on screen. But okay, so this is exactly, I mean, some pi out here multiplying the entire vector q, and this in n tuples is the same expression. Xi here multiplying the entire vector y. So because I am ordering the tensor basis is this ai tensor bj in the lexicographic order where j is less significant and I is more significant. So the ijth coordinate out here will look like this. So the entire n tuple in this lexicographic order will look like this. Okay. And once you choose this ordering of the coordinates, the natural definition of tensor product looks like this. Again, the more significant coordinate is outside, which is now the ij. Okay, and the least significant, which is kl, is inside. Is this clear, Hari?
So when we say a particular ordering of the coordinates are referring to the basis that we have chosen, like
yeah.
Okay.
Okay, yeah, I mean, I couldn't fully get it. We were cracking, but yeah. So
no, what he's asking is whether when we are writing the Euclidean representation, and do we fix a basis? Yes, yes, we do. This is the AI tensor BJ basis.
Yeah, it is AI.
Yeah, this is the basis. Yeah.
Yeah, it is the basis. And remember, to define the tensor product space, we have to first fix basis for A and B. It's a basis dependent definition. Okay. I mean, there is a basis independent definition. I mean, we will not, most likely we will not need it in this course. I'll try to avoid that. But yeah, I mean, you can read it up on your own in your free time or something. But yeah, so to define the tensor product itself, that's why I emphasized it by the formal span word. This is the tensor basis. At this moment is nothing but symbols, and I take formal span, which is also symbols, but those symbols have a vector space structure. So it's slightly abstract already. I mean, even though I'm fixing basis, the basis different definition is also slightly abstract. But yeah, once I write things as coordinates, you can say that, oh, okay, I mean, if all I want is coordinates and tuples and all, then it's clear what it is. Like x is an m tuple, y is an n tuple, and the tensor product of two vectors is an mn tuple, and the mn tuple I choose this order. And once I choose this ordering, I would like to define the tensor product of matrices also. So this matrix acts on the system A, right? So rho will act on m tuples. Sigma acts on system B, so sigma acts on n tuples. So this is the m by m matrix, this is the n by n matrix. Let me write it down. Just remember, this is m by m, this is n by n, and now the tensor product will act on the tensor product space, which is of dimension mn. So this is the mn by mn matrix. But if I write the mn dimensions in the lexicographic order, this is the form of the tensor product matrix. So yeah, more questions. I mean, this is slightly, these are slightly abstract definitions.
And I have a comment which might help, I guess. So I mean, while working, I think the abstract definition doesn't quite help. I mean, I know the abstract also. I think the most helpful one is this. Basically, you think of two vector spaces and think like this, that you have two vector spaces and fix the basis for the left guy, for the vector space in your left hand, and go and attach another vector space to every basis element. Go and attach the vector space you have in your right hand to every basis element that you have in your left hand, and that's exactly what is happening here.
Yeah, so
it's like you're putting a vector space on every basis vector, but then you might ask you, what is the basis for this new space? And then it becomes obvious. Basically, it's like a tree. So the first level of the tree, you look at the basis of the left hand vector space.
Of A, yeah. So use the symbol. Yeah, of A.
Of A, and then second level, you look at the basis for B.
Yeah.
While working, this picture helps.
Yeah, so fair picture. So basically, for every basis vector AI in A, okay. So remember, like, so for every basis vector for AI, so the I here is the ith basis vector. To that, I'm attaching an arbitrary vector from B. So I'm attaching the entire vector space. Okay. This is the tensor product. Okay, and we saw last time that not every vector in A tensor B is of the form X tensor Y, right? So we saw that not every vector. So this is where we were stopped. AB is of the form X, A, X, and Y. So these are called the entangle vectors. Okay, and the others I'll call the tensor product vectors or tensor vectors. Entangled vectors. So yeah, this is where we stopped. Like, I hope this refreshes some memory. More questions? Okay, so now we'll start some new stuff. So, yeah. So, in fact, I mean, I'll again remind you of famous example of tensor product space and entangled vector. So I'll take C2, tensor C2. So this is the two-dimensional space for complex numbers. Okay, and then for C2, I'll choose the standard basis. 1, 0. By convention, this is called ket 0, this is called ket 1. Okay. So span of, and now so this I'll call system A, the first C2 is called system B, and there's this famous vector which is called the EPR vector on the system A. So Einstein Podolsky Rosen state. So this is defined to be if you want to normalize it to a unit length over square root 2. So in terms of n tuples, it is this vector. And this vector is an like the canonical example of an entangle vector. You cannot write phi as so phi AB is cannot be written as XA tensor Y. Okay. And not just that, phi is like in a sense the most distant. Like you look at all vectors of the form XA tensor YB, and this EPR state is a vector which is the farthest from all these tensor product vectors. So in that sense, it's the maximally entangled state. So these things will make more and more quantitative sense soon. Okay, but like I mean, some geometric sense, there's already nice geometry here. This vector is farthest in, let's say, the Euclidean distance from the set of all these tensor product vectors. Okay, so let's go ahead. So back to the thing. So I have told you what, yeah, and right. So we started off with the product of two probability distributions, defined the quantum analog, the tensor product of two density matrices, and then we saw, I mean, this definition is with respect to a particular ordering. Now, let us do the reverse. So what do I mean by the reverse? So let's see. So this is another abstract concept. It's a linear algebraic concept, but it's usually not done in the linear algebra course. So I have to do it now. So let us say I have P is a probability distribution A. And again, as you know, like not every probability distribution can be expressed as a product of two probability distributions. So that way, I mean, what I wrote here should not be a surprise, or what I wrote here that there are entangled vectors here should not be a surprise, because not every probability distribution on AB can be written as PA times P. Right? These are the joint distributions, okay? And so I should remain here. So this is not FP. Excellent. Let's call it abuse notation. Why am I using get? This eraser button also behaves like a type.
You're on Windows, Cap.
Yeah, I'm in my office desktop.
And what is the writing pad that you're using?
Something called XP pen.
Oh, you don't have this thing. You don't have the Wacom ka thing.
No, this is not Wacom. This was cheaper than that. Just let me disconnect this thing and bring it. It's a problem with external, not with the right hand part.
Why don't you use the original journal, not XPP? XPP has a tendency of going crazy on Windows.
Well, normally I'll not use Windows Switch. Not today. I do other official work in the office. Okay, not every probability distribution on the system AB can be written as this is one, right? Some PA times. So we know that there are truly joint probability distributions which cannot be written as a product of two probability distributions, right? Okay. So now let us say I have a probability distribution on AB, arbitrary probability distribution. Okay, maybe it is product, maybe it is joint. I don't really care at this point. Now, from here, I want to talk of what is the marginal on A, right? And normally it is denoted by PA. And what is the definition of PA? So PA on the probability given by PA on the sample point I is defined to be summation over Ij, right? So j equal to 1 to n. Right? So I sum over the probabilities of I comma j. Okay, I sum over all the possible j's, and this gives me the marginal probability of I. So this forms a probability distribution I, which I'm calling the marginal PA. And similarly, I can define the marginal P. Right? So this is all we know. Hari? You follow it till this point?
Yeah.
Yeah. So now we're going to define the quantum analog of it. So what would that mean? So I have a density matrix on rho AB, and I want to define marginal on A, which again, I'll adopt similar group which I'll call rho A. So rho A so remember rho A will be an m by n matrix. Yeah, just a second. Okay. Yeah. So rho A, the margin on A, so it just through a density matrix, so it will be an m by n matrix for sure. So I have to tell you what is the. So I have to tell you what is the ijth coordinate out here. Okay. So the ijth coordinate here will be. So this is, let's say, this is the ijth coordinate. So this is defined to be sum over k going from 1 to n. So I'll take rho AB. And remember, rho AB was a, so let me draw it somewhere here. Rho AB was some density matrix, so it was Mn by Mn matrix, right? Mn by Mn matrix. And remember, like AB is a tensor product space, so the rows are indexed by Ij. Okay, I running over the computation basis of A, J running over the computation basis of B. The columns were indexed by KL, K running from 1 to M, L running from 1 to N. Okay. So rho AB if I have to specify an element of row AB, I will specify it by ij, comma kl. Okay. So now I want to specify what is the ijth element of row A. So that is, go to row AB and take the ijth. Stupid. IK, JK. So this is the formula. So remember, I want the ijth element of row A. So analogously, I wanted the ith element of PA. Okay. So how did I get the ith element of PA here? I looked at the ijth elements of PAB and I summed over all J. So
shouldn't there be a summation over L also?
no. So hold your guns. Yeah. So
okay, got it.
yeah, okay. So to get the ijth element of row A, I'll go to row AB and I look at ik, jk elements. So in general, I should have looked at ik, jl elements, but for the purpose of taking marginal, I'll have to take k equal to L. So that's why it's ik, jk. Okay, ij is coming from here and k is the running index. K runs from 1 to n. So this is the expression. Okay, so let me write it down formally. In other words, all that I'm saying is row A ij is defined to be summation k equal to 1 to n row AB ik jk. Ik jk. Let me get that. For the matrix ik jk.
Pranab, if you're writing something, it's not visible. I think the screen is stuck.
Screen is stuck. Okay. Stupid external. Let me minimize and open. Is it visible now?
Yeah, I can see your mouse pointer. Yeah, I can see the mouse pointer moving. Yes.
But you cannot see what I've written there.
You have written row ij summation k from 1 to n. That thing,
Yeah.
right?
Yeah.
Yes. Now it's visible. Yeah.
Okay. Maybe it's some network lag. Honey, can you see the formulas?
Yeah.
Yeah. Okay, so this is the formula. So it's kind of similar to this. Okay, of course, now here things are simple. There was only one coordinate I. Now the I has become ij, and the second coordinate was j here. So that's fine. The second coordinate, there would have been 2 second coordinates. If you're naive, maybe you'd have thought that there's a k here, there's a L here, and there's sum over all of that. But no, I have to keep the same k here and here. So this is the formula. So this formula is okay. It's actually, I mean, we'll understand what it is. There are nice linear algebraic consequences. So this is called the partial trace. Okay. And what I've done is what is called trace out B. So row AB was a matrix on the system A tensor B, system AB. And if I say trace out B, the result will be the marginal on A. What remains behind is the system A. So it's called partial trace because I'm only tracing out B, I'm not tracing out A. So why is the name trace coming? So what would be a complete trace? So the usual trace is the complete trace. It's the full trace, if you want to say. So the full trace. So in the full trace, what would you do? in the full trace, the running index will be the full index. So actually, whatever I put here to the left of the comma, I have to put the same thing to the right of the comma. So the full trace would have been ij, comma ij out here, and that will give me some complex number. Okay, so it will actually give me 1 because these are density matrices. But this definition of the partial trace makes sense for any matrix. So the full trace is a special example of partial trace. So what? So the trace means that I put the same index for the row and the same index for the column. In the full trace, I put the same index to the left of the comma, same index to the right of the comma, and what I get is a number. In the partial trace, it's not the same index does not occupy all the space out here. The same index is k, but then there is some remaining part which is I here and j. So in that sense, I'm only doing the trace operation over the system B.
You're basically doing traces on blocks of the matrix, off diagonal blocks.
Yes. So I'll draw pictures and it's going to be clear. So I'm only doing the tracing over the system B. A I'm leaving untouched, and A leaving untouched means I have to allow both I and J here, row I, column J. So I'm allowing row I, column J, every I, every J allowed. Okay, but the B coordinates I'm forcing the same K out here and I'm summing it up. So as Shantanu just said, like more pictorial what this means. So row AB. So how does it look? So of course, like this is indexed by IKJL, right? But now what I'm looking at is I'm looking at the ijth block out here. So ij block. Okay. So I fixed I and j, but k and l are allowed to vary out here. Okay. So this is over the system B, because remember k is a B index, I is the A index. So similarly, J is a A index and L is a B index. So maybe write it down. So I is A index, K is B index. And similarly, the way I have defined the ordering in the tensor product, this is A index, L is a B index. Okay. So when I fix the ijth block, I fixed the row and column index for the system A, but the row and column index for the system B is allowed to vary. So KL is out there. So these are B indices. Okay, so this part of the block, okay, is acting on the system B. And what I'm doing is I'm just taking the trace within the block. So I'm just adding up the diagonal elements out there. Okay. So that was this IK, JK. So I add it up. So in other words, what I'm doing is take the full matrix AB, but break it up into blocks. Okay. So the blocks act on the system B. The names of the blocks are indexed by IJ, where I and J are indices for A. And now I take the trace in each block. So that's why partial trace. Trace in each block. Full traces when the entire matrix is one block and I take the trace. So the result of taking the partial trace, what will it do? It will collapse the block that was acting on the system B into a complex number. Okay. So essentially what I get is a M by M matrix indexed by IG. So is the definition now clear? Right?
Yeah.
Okay. So let us, okay. So now, I mean, it requires considerable insight to understand why this is the correct definition of the marginal. So which you'll slowly develop as our course proceeds. But let us look at some properties of the partial trace out here. Algebraic properties of partial trace. So now let us say I have M on the system A. Take a general matrix.
Sorry, I have a question. So you said that why this is the correct definition. I mean, correct definition with respect to what? With respect to physics or applications in math or information theory?
Well, I mean, ultimately, all this math and information theory is coming from physics. No, I mean, we'll only do the information theory which is allowed by physics. We'll not do any unphysical information theory. Okay, and we'll only look at those mathematical expressions which model the underlying physics.
Hmm.
So in view, yeah, so of course, I mean, we'll not really do too much physics. We will always argue in terms of information. You will slowly realize that this is the correct definition to use for the marginal.
In one line, can you say why? Because I till date, I don't know why this should be correct, but like it works in everything that we do.
I will utter that one line maybe by the end of the lecture.
Okay.
Okay. So I have to define what are measurements before that. So that's the problem.
Oh.
So far, I've not defined measurements. So once I define it, then it's quite clear. But I mean, these expressions that you see are all helpful when we come to measurements. Yeah. Okay. So one of the properties is, so this is what so this is a notation. Okay. So before I do this, write down. So you should trace I denote by TR, and rho A, okay, is this operation, as I said, is trace out B. So I put a subscript B out here. Okay. So this is what I mean by the tracing out B. So come to this block. Now let us look at some properties of this. So let us see what happens if I trace out B of this. Suppose my matrix is already a canonical product, MA tensor N, and I trace out B. So what am I going to get? So you can easily check that this is MA times the scalar, which is trace of N. It is proportional to MA. And this block picture makes it clear, right? So if I do canonical product of matrices, what do I get? Okay, I get a matrix in the system AB, but then if I break it up into blocks, the ijth block, what do I have? I have the whole NB is sitting here multiplied by MIG, right? So in other words, all I'm saying is that this matrix is equal to something which looks like this. So there's this block out here. This is the so this is MIJ, and this matrix is M. So this is how the canonical product look like. And now the partial trace is saying that, okay, go to that block and just take the trace of that. So the trace of that will be Mij times trace N. Okay, so in other words, I'm multiplying each entry Mij by trace. So that just proves this formula. Is this clear? Honey?
Yeah.
Yeah. Okay. So in particular, if I took density matrices, okay. So yeah. So in particular, if I took density matrices, so if I had trace B of rho A, that's sigma B. So remember, these are the analogs of the product probability distributions. So I know trace of sigma B is 1, so I'll just get rho A. So what is this telling me? This is telling me is that if I take a product density matrix and I trace out, so trace out is basically I ignore, okay, the system B. What is the marginal on the system A? It is rho A, as it should be. So back in the world of probability distributions, if I have PA times QB, product of probability distribution, and ask, oh, by the way, what is the marginal on the system A? Then of course it is PA. So that's the same thing out. And then again, if you have to formally expand it out, as I said, like we had this picture right up. We had this picture, right? So if so this is PA times QB, and if I have to take the marginal on A, so suppose I'm looking at the second coordinate on A. So what do? I just sum over all these guys, but then this will give me 1 because summation Qj is 1. So I'll just recover P1, P2, Pn. So it's okay. So take a product probability distribution. What is the marginal on A? It is PA. What is the marginal on B? It is QB. So the same thing is going on here. What is the marginal on A? Rho A. What is the marginal on B? Sigma. But once you have joint probability distributions, then the marginal, I mean, is a non-trivial thing. I mean, from the joint probability distribution, if somebody asks, oh, what is the margin on A? I mean, you cannot often say that. You have to do the calculation and say, okay, this is the margin on A. So similarly, that is the calculation down here. If I give you an entangled density matrix, a joint density matrix rho AB, and ask what is the margin on A, you have to do this operation. Trace. Okay. Yeah. So then
I would just like to make a comment. So I mean, I just realized this. So all of this, the way we visualize it, it's extremely basis dependent. But actually, the real definition is not basis dependent, right? I mean, this way we are writing.
Yeah. So at this moment, I would say that okay. So you must have done in linear algebra why the definition of trace is not basis independent. So yeah, you have a matrix, you change basis, so you do a similarity transformation, right? You have a so let me write that down. So recall you have seen things like this: trace of A, M, A inverse is equal to trace of M, right? So this was used to justify that trace is basis independent. So trace again would have been defined as the sum of the diagonal entries. Okay. But then if you express the same linear operator in a different basis, so the matrix in the new basis will not look like M, it will look like A and A inverse, but then trace of that will be the same. So I hope you remember this. So the same thing will hold out here also. So yeah, I mean, I will, yeah, so let's say, so trace.
So for trace out, it will be like identity on the system you're not tracing over, tensor, some unitary on.
Correct. So it will be identity on A, tensor, some system B. Okay. Remember, M is now on the system AB. So, and then the inverse of this, which will be so this is equal to so let's stare at this slightly scale notation. So here is a matrix M, but now it's on the system A tensor B. It's a linear operator on the system A tensor B. Now suppose I want to do a basis change on B. So what will be the matrix with respect to new basis? That will be a similarity transformation. So what is similarity transformation? I'm only doing a basis change on B. I'm not doing anything on A. So that similarity transformation is captured by multiplying on the left by this matrix, which is identity on A, Kronecker product, the change of basis on B, and on the right, the inverse of that identity of on A, Kronecker product, B inverse. So now you multiply this out. So this is a new matrix in the new basis of on the system B. And if I do partial trace, I trace out B, same result as before. So this you can sit and check. Okay. And it's again not difficult from the block diagonal picture. So all you have to figure out is what does this matrix look like in the block diagonal picture. So,
this
yeah,
this
go ahead.
just to change the basis of system B.
Just of B, yeah.
Okay.
I mean, just this P unitary goes and changes the basis of the blocks. It doesn't affect the whole thing. It goes and it's like
no, not unitary. It is some invertible. It's similar to
some invertible matrix. It's just sitting outside the blocks, like this B block, B inverse.
So remember MAB, I'm going to break up into blocks. So the blocks act on the system B, right? So it's something like this. So now if I do the similar transformation, the analogous picture, what I'll get is because it's identity on A times, so it will be B, the same block as before, B inverse. So this is the picture. If I take MAB to be some matrix, but break it up into blocks. So this is the ijth coordinate on A. Okay, and in the ijth coordinate A, I'm looking at the ijth block out here. So the block is acting on the system B. It is indexed by k, n. And now, so this is the original matrix. After the similar transformation, what I will get is the same block here, but it's conjugated by B on the left and B inverse on the right. So now if I'm going to do the partial trace, remember I just take the trace on this block. So this trace is the same as this trace. So that's why it doesn't matter. So is it clear now? So basically, if you just expand this identity A tensor BB in full glory, and then see that conjugating gives you this picture. Okay, but that's so that let me write elsewhere how this looks like, so that it looks even more convincing. So identity on A tensor some matrix B on the system B in our Kronecker thing will look like a block diagonal matrix. The rest will be all zeros out here. Okay, and this is B. And now you multiply M on the left and right by this matrix, which looks like this. You'll exactly get this picture. Okay, any doubts about this? Okay. So this is this shows that the partial trace is actually basis independent. Okay. So it is independent of the choice of basis on the system that you are tracing out. Okay, so I mean that strengthens the intuition that it is indeed a generalization of the full trace, which I've seen. Then there are other properties out here. So remember the trace was linear. So trace of alpha A plus beta B. Alpha trace A plus beta trace B. So you can say the same thing out here. I want to do partial trace. So let us say alpha M plus beta N. Remember, just to remind you, this is on the system AB. So you can check again by the same block picture that this is alpha partial trace of M plus beta partial trace of M. So the partial trace is also a linear operator. So the usual trace was mapping matrices to complex numbers. So complex numbers are one by one matrices in this picture. The partial trace is mapping matrices on AB to matrices on A. Okay, so again, I mean the full trace was when A is a one-dimensional system and B is the full system. Okay. So partial trace on B. Once B becomes the full system, it will map it to system A, but system A is one dimension. In other words, these are one by one matrices or scalars. So again, recover this same. From here, you recover the same expression. Okay. So these are some properties of the partial trace. And it's possible to define, in fact, the trace and the partial trace in a basis independent way, but that will use the basis independent definitions of the tensor product. So we'll not get into that.
There is another way of doing it, which also helps computations, I guess, and which does not use the basis independent tensor product definition. So,
yeah, we will come to those as required.
Yeah. I think that's a little too much.
Yeah, let's stick with this thing as well, at least. Yeah. Some properties we've seen.
I mean, you understood which one I'm talking about.
I know which one. Yeah, I mean, I was debating this very second whether I should write it down, but we will do it when it comes to it.
I think the picture wala thing helps a lot more. I usually use the picture wala.
Yeah. So that's we work with pictures, blocks, and yeah. Okay, Hari, questions, please. So you haven't done partial trace at all, right? Yeah. Are you there?
Yeah. Did you ask something?
Yeah, I'm saying that any doubts about this? Yeah, this is an important concept. So
Yeah, this
take
is
some time to digest it.
Yeah.
Okay, so essentially, I mean, we have finished this picture, like we have seen how to take the marginals. Yeah, so, okay, I've defined the partial trace for sure and with blocks and all that. So one thing to check, of course, is if I'm in the world of probability distributions, I take a joint probability distribution AB and then I marginalize on A. In other words, I trace out or discard the system B. What I should get, this vector that I should get should also be a probability distribution on A, right? But then of course, is the same. I mean, if I sum over all I out here, this is the same as summing over all ij, and that I know is 1. So I have to do a similar consideration out here. So that is captured by this fact. What I'm saying is, so I have this density matrix rho AB. First I discard A, so I trace out, first I discard B, I trace out B. And now this I was calling rho A. The question is, what is trace of rho A? Okay, so trace of rho A means I'm now even discarding the system A. So this in our fancy notation is first take the partial trace over B of rho AB, then take the partial trace over A, but this is nothing but the full trace. As you can guess. So whatever matrix we are defining out here, rho A, it is trace 1. So that just follows. Again, I mean, this follows from the block picture out here. Very easy to check. What is slightly harder to check is, okay, I have defined something here for sure, rho A. Is it Hermitian and positive semi-definite? So the answer is actually yes. If rho AB is positive semi-definite, the partial trace is also positive semi-definite. Okay. And this maybe, I mean, you can sit and do it with the blocks also, but we will see kind of nicer and little more abstract ways of doing it as the time comes. But for now, I mean, it's fine that if like you just take it as an act of fate, that the partial trace operation will send a positive semi-definite matrix on AB to a positive semi-definite matrix on A. So in other words, this rho A that I have defined out here is a density matrix. So it is a valid quantum state only. So that is the full picture. Like starting with a quantum state on AB, I can I have a mathematical process which corresponds to the physical process of discarding the system B. In other words, I have a mathematical definition of what is the margin on A, and the margin on A is also a density matrix. Okay, let's go to the next topic.
Wait, did you prove this?
No, we will. You can prove it by blocks if you want.
But this is one proof where I think that
yeah, where the little more abstract methods are better. So as I come to the abstract methods, we will definitely do this. Okay. So, but yeah, I've been saying abstract methods, but I mean, all of them are basically leading to the notion of measurement. So now I have to say, what is measurement? Okay. So again, our picture, classical probability versus quantum probability. Okay, fine. I have a classical probability distribution. Okay. So let us say, okay, it will help me to consider the joint probability distribution AB. So what manipulations, what information theoretic or data processing manipulations I can do on probability distribution? So this we already saw in the classical part of the course. So we can apply private coin algorithms on them, right? I hope you remember this. We can apply private coin algorithms on that. And then when we were looking at data processing for relative entropy, okay, the good old Shannon relative entropy. So to prove the data processing inequality, we came up with a slightly strange style of proof that we said that any private kernel algorithm can be thought of as a three-step process. Okay. So on row AB, I want to do a private kernel algorithm. So this was a three-step process. So the first step was let me start with row A out here.
You want to consider the distribution along with the coin register. That was the first step.
Coin and the workspace also.
Coin and the workspace also.
Yeah.
I mean, can I use the word purification?
Well, we will, yeah, we will use such words more and more as the course proceeds. Okay. So step one was, okay, so I have this probability distribution A and I want to do a private kernel algorithm. So recall the data processing proof. As I said that any private kernel algorithm can be thought of as a three-step process. First step is attach system B, initialized all 0. Okay, so this is the workspace, okay, and the coin register. So I should all 0 and workspace and coin. So together we will call it B, called system B. So what happened? PA became some PAB, which is PA times yeah. So the tensor product will maybe just cut.
No, may not be tensor, right?
No. So no, it is a product distribution. So PA times. So there was the all zeros is just a concentrated probability distribution. So I think I used the notation 0.
You could do accept
P1
reject based on the coin register.
And this is the RB2. So this is the workspace register initialized to all zeros. Okay. So the initials to all zeros in the language of probability vectors is so if you have, let us say, 10 bits of workspace. So my sample space will be of size 2 to the 10. This, the space of all bit strings that are possible on 10 bits. So that is 2 to the 10 bit strings are possible. And now initializing to all zeros means it's a probability distribution. It gives probability 1 to the all zeros bit string and it gives probability 0 to every other bit string. So that is what this definition meant. And then there was this random coin out here from the coin workspace, which I'm calling bit. You remember this, Hari? Yeah. So now we are going to draw on that memory. And now step 2 was apply a reversible deterministic algorithm on AB. So reversible means the I mean, if I'm describing the algorithm by some function, okay, that function is an invertible function. So it's just a permutation of bit strings. Okay. So remember, this R was the private coins. Okay, but once you fix the private coins, the algorithm is deterministic. So I'm talking that deterministic algorithm, but I'm going to apply a reversible deterministic algorithm. So this deterministic algorithm creates a permutation of bit strings. The bit strings on the system A, B1, B2. Bit strings on the system A. And finally, the thing was discard. Okay. Let us say my like output space I'm also calling A. In general, the output space could be different from the input space. So, but let us say I'm talking of the output space to be the same as input. So I'll just discard whatever I had attached. So this was a three-step process which described every private key algorithm from A to A. So from A to A. Similarly, if you want from A to A prime, you can define things in that. Private key algorithm from A to A. So I hope you remember these things. So now we'll see what is the quantum analog. So the most general data processing transformations that we are going to do are private key algorithms, and they can be described by this three-step procedure. So we will draw the same analogy. So what can we do to the quantum thing? So we can attach a system B, initialized or zero workspace. Now you say, oh, and then coin together and all zero workspace and coin, and together call system B, and I'll put a probability distribution in the coin. But in quantum, as will become clear very soon, I mean, there are additional powers elsewhere. So I don't need to divide my new system B into B1 and B2. B1 I'll say is all zero workspace, B2 is the private coin. So quantum, all I need is just B. So B will, some part of B, if you want, will function the workspace, some part of B, if you want to keep, will function as a coin. But I mean, more generally speaking, the entire B is the workspace initialized to all zeros. And the effect of the coin can be captured just by an all zero workspace. So this is a big point of difference. Okay, and I mean, it will become clear slowly as you develop the mathematical formalism that we don't need to talk of a separate coin or separate like source of private randomness or anything. All we need is attach some all zero workspace. Okay, that is B. So what is happening is row A is now going from, it's now going to row AB, which is nothing but row A tensor, what I'll still call 0 on B. So this 0 on B, so what is the 0 on B? So, okay, so let us say my workspace is made up of 10 bits. So the sample space is of size 2 to the 10, all the possible bit strings. So now, what will be the Hilbert space for this? Okay, the vector space for this system, it is also the same space of dimension 2 to the 10. The only difference was in the classical world, the most that I'm going to allow are probability vectors on the 2 to the 10 dimension space. Quantumly, okay, I'm working in a inner product space, so I'll allow any complex vector on this 2 to 10 dimension space. So that's the difference. So the dimensionality of the space is the same. Like, so let me write it somewhere here. Workspace. Space. 10 bits. Probability distributions. Sample space. Strings. So and so this was classical, and in quantum it will be vectors in 2 to the 10 dimension complex space. So the space is now and the computational basis. Okay. So remember, like, I mean, we have to take an inner product space, choose a particular basis, okay, and I'll call it computational basis. So the computational basis for the purpose of a computation. So fix some basis of this 2 to the 10 dimensional space or complex numbers. Fix some basis once and for all. Now this basis I will now identify with my bit string. So computational basis indexed by strings 10 bits. So very similar, which was there classical and quantum. So classically the sample space was 2 to the of size 2 to the 10. Okay, but the most that I was allowing on that sample space are probability vectors. But quantumly, instead of sample space, I'll think of a vector space. So remember the sample space was a finite entity. The sample space had cardinality 2 to the 10. But the quantum analog will be a vector space. The vector space has infinite cardinality. Like C2 to the power 10 has infinite cardinality. But the dimension of this is 2 to the power 10. And in this vector space, fix an orthonormal basis once and for all. Call that your computational basis, and just for convenience, I index those vectors by strings on 10 bits. So this is the analogy between the classical and the quantum. And now when I wrote 0b out here, I talked to the probability distribution, which gave probability 1 to the all zero string and probability 0 to every other bit string. So here, this 0 will be the density matrix. So let me write it down. So in the same thing, 0b is the density matrix. It is the diagonal density matrix. So remember, the density matrix acts on the 2 to the 10 dimensional space. The basis vectors of the 2 to the 10 dimensional space are indexed by bit strings. So there will be the first basis vector is indexed by the all zeros bit string. Second one maybe by all zeros 1, like that. Okay. The last one is by all ones bit string. So with this ordering of the basis vectors, the 0b is the density matrix, which puts a 1 in the coordinate corresponding to the bit string zeros, all zeros bits. Okay. And every other entry is 0. You can check that this satisfies all the properties of a density matrix. This is basically the same probability distribution. Okay, so this what was this? 0b. It was this probability distribution. 1 and then all zeros. Right? This was indexed by the all zeros bit string. This was indexed by the all ones bit string. So same thing out here, and as I said, this is the von Neumann style. Like take this probability vector, but now write it in the diagonal form as a diagonal density matrix. That's it. So this is this density matrix, a valid density matrix, which I'm calling 0b. So the first step is to attach the system B. So the overall density matrix changes from rho A to rho A tensor 0. Is this step clear? Right?
Yeah.
Good. Now comes the next. So remember the prescription here is apply a reversible deterministic algorithm on AB. So what I do is the quantum thing is apply.
Question.
Yeah, question.
Can you scroll up a little bit?
Yep.
So this complex space C of dimension 2 to the 10.
Yeah.
What is this analog of?
This is the analog of the sample space. Okay.
Okay, so now we are allowing like each and every element to be a complex.
Well, so what is the most general information processing object that would allow this sample space? That will be a probability vector, right? A 2 to the 10 tuple, a probability vector. That is the most general object that will work. Mathematically, the most general object that will work with here will be 2 to the 10 by 2 to the 10 density matrix.
Okay.
That's the thing. So yeah, I mean these things will make more and more sense, like as I define more the formalism. But as I said, like fine, I mean, right now I'll say, okay, I mean, this is one point of difference, but I mean, is that all? Yeah, that is all. It's actually a big point of difference, but there is some analogy also, like the set of all your bit strings indexes your computation basis. So, so that is where the computation or the information processing comes in. Like on your quantum system, if you want to use that quantum system for the computation, okay, at some point you will have to express things in terms of basis, and then you'll say, oh, this basis vector, this basis vector in my identification corresponds to the bit string 0, 1, 0. Okay. Or I'll say, okay, I do something else and I write down the matrix and analyze this entry. Say, which is this entry? Ah, this is the entry. This is the entry somewhere here. Okay, it is indexed by row basis vector 0, column basis vector 1, 1, 0. Okay. So you'll say, okay, yeah, row basis vector 0, 0, 0, column basis vector 1, 1, 0. Okay, this is basically my classical way of whatever, my classical lens on some quantum state. So yes, so how it will be done in a physical system? I will come up with some quantum system whose inherent dimension is 2 to the power 10, and we will soon see examples, very natural examples, which will where the inherent dimensions will look like powers of 2. So really, I mean, the fact that computations are all done using bits, the binary system that has clear analogs in quantum systems. So there are quantum analogs of bits called qubits, which you may have heard of. So it is very easy to come up with physical systems whose inherent Hilbert space to describe its quantum mechanics is of dimension 2 to the power 10. So take any one such system. Okay, so the mathematical description of the system involves a vector space of dimension 2 to the 10. Fix a basis of this. So which basis you will do in a real experiment? You'll choose a basis which is most convenient for experiment. Okay, so you take that basis and then in that basis, in some order, you identify it with the strings and tangents. So this is how I will relate like information aspects or whatever, the computational aspects to physical aspects. Okay, the computational aspect was the bit string. The physical aspect is which basis vectors. Yeah, but then if I have to fully understand the physics, I cannot work with probability vectors. Okay, I cannot work, in fact, with vectors on. I cannot work with vectors of size 2 to the power 10. I have to work with 2 to the power 10 by 2 to the power 10 density matrices. That's all. So if any additional processing power will come because I'm working with more general objects. Okay. Okay, does this clarify some of your doubts?
Yes.
Okay. Yeah. So the first step was this, that rho A tensor 0B. 0B is just this density matrix. I mean, it's almost the classical probability distribution. It's just that my notation here is different. I'm no longer thinking of probability vectors. I'm thinking of density matrix. Okay, fine. Attach it. Now, the second part was apply reversible deterministic algorithm. So the quantum algorithm apply a unitary transformation, a unitary matrix. Transformation on A. So remember, a unitary transformation is an invertible transformation, always for sure. So the analogy, okay, this reversible thing was like it's a permutation of bit strings. So the analogous thing here, it has to be at least invertible. But I mean, you'll not get the correct physical interpretation if you allow all invertible transformations. So physics says that what we can apply unitary transformations. Any unitary transformation is a physically realizable thing in the laboratory. We can apply that. Okay. So what was the classical reversible deterministic algorithm? It was a permutation of bit strings. So permutation of bit strings. Okay, so let me give an example. Let us say I take bit strings of length 3. and more space for this. Do it below. So I want to convince you that a permutation of bit strings is actually a unitary matrix once you view things the right. So let us see. So let me take this permutation of bit strings of length. So 0, 0, 0 goes to 0, 0, 0, 0, 0, 1 goes to, let us say, 0, 1, 1. Then 0, 1, 1 goes to, let's say, 0, 1, 0. Then 0, 1, 0 goes to, let's say, 1, 0, 0. 1, 0, 0 goes to, and complete the cycle 0, 0, 1. What remains? 0, 0, 1, 0, 1.
101.
Yeah. So 101, let us say, goes to 110. 110 goes to 101.
And 111.
111 can only go to 1. So here's a permutation. Let us say my reversible deterministic algorithm working on the system AB. System AB happens to be described by 3 bits. Okay. Does this permutation. Okay. Now this permutation I can actually write it as a matrix. Every permutation can be written as a matrix. So this will be a 6 by 6 matrix. Sorry, 8 by 8.
8 by 8.
Yeah, it will be 8 by 8 matrix. So rows and columns are indexed by the bit strings. So I use lexicographic order on the bit strings. So similarly for the columns. So this is exactly, I mean, how you map a linear transformation into a matrix. So 0, 0, 0. So the basis vector 0, 0, 0 goes to 0, 0, 0. So I put a 1 here. And everywhere else I'll put zeros. So I'm not going to write them. 0, 0, 1 goes to 0, 1, 1. So I'll put a 1 out here. Then 0, 1, 0 goes to 1, 0, 0. So 0, 1, 0 goes to, so I'll put a 1 here. And then 1, 0, 0 goes to 1, 0, 0. So the column 1, 0, 0 will go to 0, 0, 1. So I put a 1 in this position in the second row. Okay. Then, oh, I forgot 0, 1, 1 goes to 0, 1, 0. So that is here. Then 1, 0, 1 goes to 1, 1, 0. So that is here. 1, 1, 0 goes to 1, 0, 1, which is here, and 1, 1, 1. So this is the matrix. So once I draw this matrix, so if I apply this matrix on, let us say, the basis vector 0, 0, 1. So remember the basis vector 0, 0, 1. So show one example. If I apply it on the basis vector, so what is the basis vector 0, 0, 1? I'll emphasize it by the cat notation. The basis vector 0, 0, 1 is when I have 1 in the 0, 0, 1 position and zeros everywhere else. So I take this matrix, apply it on this vector. Okay. Then what do I get? I get the second column out here. And the second column is the 0, 1, 1 vector. So this matrix, this matrix multiplying the vector actually realizes this permutation. So such matrices are called permutation matrices. So permutations, once I denote them as matrices, they become linear transformations. And the property of this permutation matrices is that they have position, they have a 1 in exactly, they have a single 1 in every row and every column. exactly a single one in every row and every column, which you can. Okay. Conversely, you take any matrix which has exactly a single one in every row and every column, other entries being 0, you can think of it as a permutation. So this you may have seen here. Is this clear? So the permutation, so the reversible deterministic algorithm, the permutation, I'm now expressing it as a linear transformation of permutation matrix. Is this example clear?
Yes.
Yeah. So the quantum prescription says that, so this is where the additional power of quantum is coming. So physicists say that, oh, in the quantum world, you don't have to just apply a reversible deterministic algorithm. You don't have to apply just a permutation matrix. You can apply any unitary matrix out here. And you can see that permutation matrices are unitary matrices. I mean, take any two columns, for example, they're clearly orthogonal, and each column has length 1. So, so this is where, I mean, reversible algorithm is a special case of unitary transformation. Okay, and now I'm finish the picture, which is the third one. So, third one is discard B means trace out B. So, this is the what I mean by the most general transformation that I can do on a quantum system, on a density matrix. Okay. So this is the perfect quantum analog of this classical thing. So attach a system B initialized to the all-zero workspace. As I said, and we will see soon, is that I don't have to talk of a separate coin space anymore. Okay. So why is that? The effect of the coin can be simulated by more workspace and by changing the unitary transformation out. So this will, this we will see explicitly soon. So I don't need a separate coin space out here, just all-zero workspace good enough. Now, instead of permutation matrices or reversible deterministic algorithms, here's where the extra power is coming. You can apply any unitary transformation maybe, and discard B is basically the same. You do the analogous operation to trace out. So,
I mean, this is absolutely fine. This is indeed the most general quantum operation, but emphasis on the word quantum operation, because if you measure and observe, then things are different.
Well, yeah. So
and measure and observe is like this observe thing. I don't know physically what it means, but yeah, it's different. It's something that I don't know classically nahi hota.
Yeah. So you're saying what is the measurement of quantum systems? So yeah. So definitely, I mean, we'll have to study that. But as of now, what I'm saying is, so here was the most general operation that I'll do on a classical system, the private core algorithm, and here is the most general operation, the analogous I'll do on a quantum system. So all these observation measurements, I mean, will be subsumed by this as we will see mathematically. So in quantum information processing, this is the most general operation that I'm working on. So there's a name for it. Here, so these are called quantum operations. More fancy names are completely so because of whatever other reasons, there are terms here called positive trace preserving. So short people write CPTP, completely positive trace preserving super operators. So the short name, which is very much used in literature also, quantum operations or general quantum operations, if you want to emphasize that this is the most general thing that I'm going to do. Okay. And if you want to, use technical jargon and so it's also called completely positive trace preserving, sometimes abbreviated as CPTP, super operators. Okay. Sometimes called CPTP maps, okay. CPTP operations, super operators. Anyway, but we don't care so much about jargon, so we'll call it quantum operations most of the time. and this is the most general quantum operation that we are doing. Okay. So questions, right? Okay. So if not, let's go ahead. So let us see what we are going to do with a quantum system. Now we really want to use our.
Pranav, are we having an extended class today?
Oh no. What's that? Okay, then stop. This is a good stopping point here. So
Actually, sorry, I actually have to meet somebody at 1:30, the Singapore guy. So.
oh, okay. Oh yeah. So we start 11:45. Yeah. So we have done the good point. Yeah, this is a good stopping point. So we have seen what is the quantum operation, and next time Thursday we will go ahead. I mean, now we are really getting deep into what are the data processing operations you can do in quantum. So the next thing we'll do is measurement. Measurement is a special type of quantum operation. But yeah.
No, but so I've always tried to make a distinction here. So measurement, if you don't observe, I mean, if you don't observe, then measurement is a quantum operation.
Even if you observe, it all fits into that.
After collapse, remember, like trace is not like, I mean, we know this from our work, right? If you observe, then suddenly you have to divide by a number smaller than 1, so trace down.
Yeah, but they're all captured in this formalism.
Achha.
You just have to, set up things right. They're all captured. I'm not lying when I say that this is the most general quantum operation.
Okay.
But measurement is sufficiently important in theory and practice both. If you want to do in the lab, you do some operation, and then you want to really do an observe in the English language sense, because you have to make sense of what you have done.
Mm-hmm.
So how do you capture this English language word observation by your actual operations in the lab? So what you do is a special type of quantum operation, which is called measurement. It's very important in both theory and practice. Okay. So, we'll have to, of course, define it, and we'll have to keep coming back to it all. And every time we'll say measurement. You cannot do quantum computing or quantum information theory without uttering the word measurement like in every third sentence. So, yeah, it's very important.
No, I just have one question. So suppose you have a measurement like pi and I minus phi. Okay, and you just want to say that, and say pi happens with 1 minus epsilon. So you want to say that if you apply pi, what do you get? Pi rho pi by 1 minus epsilon. Right? So we can't apply data processing inequality just to pi, right? No. You have to apply data processing to pi and I minus pi.
Correct.
That's correct, right?
That's correct. Yeah.
So
that's
when I said, so when I said measure and observe, what I meant was the first case, that you see pi, but you only want to apply like data processing to pi. Okay, not the whole thing. That is not possible. Yeah,
that's not. That is, I suppose, what you mean by collapse. Like
collapse. Yeah.
That's again something collapse. Which happens classically.
Collapse happens classically.
Yeah, you do something, then you condition on a particular bit being something. That's the same thing. You observe that bit, you
observe, and then you normalize by the measure of
you observe the bit, say, oh, it's 0 now. I'll henceforth proceed assuming that it's 0. So we'll not renormalize by.
Yeah, I know that picture. Yeah, I know that picture.
Yeah. So it's still the same thing.
So basically, it's like dividing by the trace of the thing is like normalizing by the measure of the space that you're conditioning on.
Yes.
Okay.
Yeah. This is perfectly analogous.
Okay. Got it.
Yeah. So really the extra juice is coming from here, this unitary transformation. Okay. The others are very much analogs.
Pranav, I have to go. Okay. I'm sorry about this. This guy has sent the link. Okay.
Yeah. Hari, questions?
This is fine.
Fine. Okay. So we'll stop now. Meet on Tuesday.